Our subject today is isotopic fractionation, and what that is the process by which heavier and lighter oxygen isotopes are separated from the ocean by changes in temperature. The red isotope you see in front of you is oxygen-18. It has 2 extra neutrons than oxygen-16, which is the blue animatronic hand in front of you. That means that 18 tends to stay in the ocean and 16 tends to get evaporated.
To elaborate on this more, studies have shown that the ratio between oxygen-18 and oxygen-16 isotopes is about 1 to 500. This means that the heavier oxygen isotope is more rare.
In the oceans, they'll begin to evaporate, and the 16s will go up much more plentifully than the 18 because they're heavier. And then they head towards land, and they make landfall. So as they go across the land, the 18, because it's heavier, will get rained out first because it's heavier. That makes sense. And then the 16s will continue onwards and move northwards until they're eventually rained out as snow, and they pack together, becoming giant glaciers. And so now the 16 is being stored in the glaciers, whereas the 18 is still in the ocean. So the percentage of 16 to 18, there's more 18 in the ocean, therefore the percentage is higher of the 18 in the ocean.
During periods of Earth's history with higher insolation, all that O16 that was trapped in glaciers melts and flows down rivers into the sea again.
Temperatures rise, all the 16 is returned to the ocean, and there's only one O18 per 500 O16s. So there's far more 16 now in the ocean. And so now we can tell that it's either cold or warm simply by the amount of O18 to O16 in the ocean.
During periods of warmer temperatures on Earth, more oxygen-16 isotopes are present in the ocean. This can be calculated with various climate proxies, such as deep ocean sediments. In the formation of their calcium carbonate shells, benthic foraminifera utilize the elements around them to produce growth. Benthic shells found in ocean depths with historically high O16 concentrations have shown to be more smooth as compared to that of one that lived in waters with a smaller O16 concentration. This means that organisms that had to utilize water with a larger ratio of heavier oxygen isotopes had deformed shells. This serves as both an indicator of global climate on Earth at a specific time, as well as a look into the metabolisms of early life on Earth. To explain this ratio we keep referencing, deep sea sediments are examined for a ratio of oxygen isotopes. This is known as delta 18, and the entire ratio is represented as this value. In this ratio, we compare the heavier, rarer oxygen isotopes to the lighter, more common oxygen-16. To get an accurate measurement, the ratios are compared to the Vienna Standard Mean Ocean Water. This provides a baseline for deep sea core samples to be measured from. This means we are always looking at the levels of oxygen-18, as this comparison of isotopes is the main indicator of temperature on Earth. As previously stated, in periods of warmer temperatures on Earth when ice sheets were relatively smaller, this would mean that the ratio would be smaller as well because many oxygen-16 isotopes are located in the ocean. However, when delta 18 is in higher concentrations, this in turn means that the heavier isotopes in the ocean would stay there while the lighter ones would remain in ice sheets on land. Therefore, that during glacial periods, the delta 18 concentration ratio will be higher